gratitude and also extend a very warm welcome to our judges for the physics deep thought, Professor Saurabh Dubey and Dr. Surbhi Jaiswal. And they were present throughout the framing and the verification of the questions. And I would like to thank them on the behalf of the question making team. We have our teams. We have IISc, we have team IIT Bombay, we also have team IIT Delhi, and we have team IISER Kolkata. For the audience, for the participants, and also for the judges, I would like to very briefly go through the rules. The total time for the deep thought is going to be 2 hours and 30 minutes. There will be a total of 4 questions in this deep thought round. And for this specific deep thought round, the judges will be drawing a chit, and the team which is selected will be presenting the first question, and then we'll be following the clockwise order, wherein the next team will be presenting the second, the subsequent team will be presenting the third and the fourth questions. So this will be a fixed order round. Apart from that, as you guys are aware, that so after the podium coordinator will finish presenting the question, the 15 minutes timer will start, wherein you can think and you can work on your solutions, but you cannot present on the board. After this, the first team will get 5 minutes to present on the board. The subsequent teams will get 3, 2, and 2 minutes. The maximum marks a team can get if they answer the directed question correctly is 15. And the last past question for a team, the maximum marks they can get is 10 marks. Apart from this, you guys are aware that please add new information to your solutions. If you repeat solutions of the previous team, they will not be considered for evaluation. And also you are aware about the clarification system. I think I think you guys are aware about the format, we can start. So now I call upon Sumangalam and Tanishq, the physics deep thought podium coordinators, to take the event forward. Thank you.
Good morning to all. I welcome everyone to the Physics Deep Thought of Mimamsa 2025. My name is Tanishq Agrawal.
And my name is Sumangalam Sharma. We'll be handling the podium for this round.
We'll first like to introduce our judges. We have Saurabh Dubey and Surbhi Jaiswal, both of whom are faculties in the physics department at IISER Pune. Saurabh Dubey is an experimental particle physicist, and his primary research interests are the searches for particles not described by the standard model.
Surbhi Jaiswal works in the field of plasma physics, and her research centers around complex plasma, also known as dusty plasma. We thank both of them for being here today.
We request our judges to pick a chit to determine the team that gets to answer a question first, and we'll proceed clockwise from that team. So, IISc Bangalore has got the first position. So, the order will be IISc Bangalore, IIT Bombay, IIT Delhi, and then finally we will have IISER Kolkata.
Now we're all set for physics deep thought. I'll start by reading out the names of each question. We have Rest in Pieces, Et tu, bru-tine, Woe betide you, Everything, Everywhere, All at Once. Team IISc Bangalore, you'll be going first. You don't get to choose.
The order is fixed for this.
The order will be fixed for this round. We'll be going with Rest in Pieces. Each subsequent team goes with the corresponding order of the question. We'll be beginning with the first question, Rest in Pieces. Aboard the spaceship Athena, the crew battled the extreme environments of outer space, along with the tedium of the regular upkeep of the ship. On one of the cleansing missions on the ship, the humanoid robot Samangalam 09 Vatar 85 Sharm uses a pitchkari that shoots liquid. He observes the stream of liquid from the pitchkari breaks off into smaller droplets with time. To better study this phenomenon, he decides to perform a controlled experiment. He creates an approximately cylindrical stream of blue liquid of very long length and radius approximately r0. The cylinder is not moving with respect to us at the moment. Imagine initially that a standing wave of small amplitude is present on the curved surface of the cylinder, perturbing the radius in the following manner, given as r of z is equal to r naught plus epsilon cos 2 pi by lambda z, where epsilon is less than r naught at t equal to 0. The pressure difference across an air-liquid interface due to surface tension S is given by del P is equal to S 1 by R1 plus 1 by R2, where R1 R2 are the radii of curvature in perpendicular directions at that interface. Question 1. Will the deviation, that is from R0, of the shape grow or decay with time for the lambda listed below? Will there be different rates of shape change? Assume that the lambda does not change with time. We have case 1 as lambda greater than 0 but less than 2 pi R0, and case B, lambda is greater than 2 pi R0. Now, consider a long stream of liquid with an approximate radius R0 and exact radius at t equal to 0 given by r of z is equal to R0 summation epsilon k cos 2 pi by lambda k z, where k varies from 1 to n, where epsilon k is greater than 0 and less than R0, and lambda k is less than lambda k plus 1 but greater than 0, where n is some large integer and lambda k lie in a large range. Question 2. Give an explanation for your expectation of the size distribution of the droplets formed. Team IISER Bangalore, do you need any clarification regarding the question? Team IISER Bangalore, will you be needing any further clarification? Okay. You will now have 15 minutes to go over it. Your time starts now. Team IISc Bangalore, you have 5 minutes left. Team IISc Bangalore, you have 1 minute left. Team IISc Bangalore, please come on the stage. You have 5 minutes to present your solution. Your time starts now.
So we have the radius of curvature of the cylinder oscillating in as a sinusoidal wave. So the expression of the radius will be with r of z equals to r naught plus epsilon cos 2 pi by lambda z. Now when lambda is much lesser than 2 pi, when lambda is much lesser than 2 pi r naught, the oscillation will be very rapid with changing z. So the radius of curvature at these points, will be negative, and not only that, here because the radius is changing very rapidly with increasing z, so here the radius of curvature will be more negative. Now del s equals to del p equals to s by 1 by r1 plus 1 by r2. Now here the radius of curvature is negative, so we can put 1 by r1 at r of z at this point. If the radius of curvature is this point as r of something s, then it will be minus r 1 by rs, because rs is negative here. Now because when the oscillation varies rapidly with z, rs is much more in magnitude, so the overall pressure will become negative. So at this point it will gradually, since the pressure is negative here, it will the troughs will become more deeper and the crests will become higher. So eventually with time they will grow like this. So the oscillation will grow with time, and it will expectedly form a droplet. Now when in the second case, when lambda is much greater than 2 pi r naught, the oscillation varies slowly with respect to z. So here the radius of curvature, the magnitude of the radius of curvature of rs will not be very much. So the overall pressure will not go as negative as that, and slowly it will decay with time, not grow like that. And this is the answer to the first part mostly. And if we go to the second part, then we have that the radius r of z is varying as r naught plus summation k equals to 1 by n epsilon k cos 2 pi z by lambda k. So in that case, so if we plot this will approximately look like the Fourier expansion of a particular periodic function. So if r naught is this, it will vary like this. And how much this height is, this depends on the individual values of ek. And so going by our previous explanation, where there is the decrease from r naught, there will be negative radius of curvature there. So the drop is expected to collapse there. The liquid flow is expected to collapse there, and there the droplets will form. And now, depending on the individual values of ek, the size of the droplet will vary. If the magnitude of ek is more, then the droplets will be bigger at that point.
And he is deriving.
You can see that the double derivative of this expression, the radius of curvature will depend on the double magnitude of the double derivative of this expression, and the radius of curvature, if we find that expression, that will be epsilon into 2 pi by lambda whole square times cos of 2 pi by lambda times z. Qualitatively, the radius of curvature will be maximum at wherever r is maximum, and it will be minimum wherever r is minimum.
Team, you have 1 minute left. Team, your time's up. Thank you. Next, IIT Bombay, you have the stage. You have 3 minutes. Your time starts now.
Yeah, so from the diagrams and equations which IISc wrote, for A part we can infer that lambda by 2 pi is much less than R naught. And like here we get a kind of negative radius of curvature for this point for the minima of the wave. So this would cause a lower pressure due to the radius of curvature of sine wave. So and since the in this lambda by 2 pi is much less than r, so 2 pi by lambda would be much greater than 1 by r naught. So that factor would dominate over any other factor, which would cause this region to be of slightly lower pressure and the maxima region to be of slightly higher pressure. It would cause water to flow from this point to this point, which would kind of like act as a dampener for the oscillations in the standing wave. It would cause ultimately for the A part to the wave to decay and wave to decay with time. For the B part, exactly opposite happens. The factor of radius of curvature 1 by r naught dominates. It would, and since this has a lower radius, the lower pressure which is caused by the 2 pi by lambda factor won't be as significant in this case. It would cause this region to be of slightly higher pressure than this region, which would make water flow from here to here. It would like kind of be a forced oscillation in the standing waves. So for the A part, we have waves, we have smaller waves, and ultimately they would damp. But for the B part, we have larger waves, and with time, these minima would go on lower and lower and ultimately form droplets. And the size of the droplets would depend on lambda and also epsilon. And for the second question, it's kind of similar to what they have answered. It would be kind of a Fourier, like we would have a superposition of multiple waves, and the size of the droplets and where it would form would depend on values of lambda k and
30
epsilon
seconds
k.
left. Team IIT Bombay, your time's up. Team IIT Delhi, you're next. Your time starts now.
Yes, so when we use the formula for the pressure difference, we get a variation of pressure which looks like this. So if we see that, we can make an analogy to compressed and stretched springs which are in series. Expression.
After binomial expansion and summing up the terms, the final delta P is coming some linear of cos plus so if we ignore the higher terms, we can approximate it to be a spring with with some rarefactions and compressions.
Yeah, so because of the pressure difference at various points, we can say that, I'm talking about the first case. Because of the pressure difference at
30
various
seconds.
points of this, there are currents which develop, and due to the collisions of the water molecules, we can say that the energy of the oscillations of this system will decrease. So the shape of the wave also decreases.
And we can also show it mathematically because there will be other terms. This would
Team, your
cause a
time's up.
decaying factor.
IISER Kolkata, you're next. Your time starts now.
Okay, so as we can see in the various points along the Z, suppose if we take these two sections from here, the points where the radius is actually higher than the positive radius is actually higher than the negative radius, so we can show that the net pressure difference will be actually will be actually towards it will be actually towards the negative side. So along these parts the waves will slowly shrink down in case of the higher in case of the higher oscillations. And when our frequency is actually low, this will lead to very slow variation, and ultimately at very large lambdas this will almost go to a constant waves. So and now for the second part, as the pressure variation is actually like this, so the droplets are going to the droplets are actually going to like break from the starting positions, and the points where and the size of the droplets will actually depend upon from where the radius breaks from here.
30 seconds.
Basically, what will matter over here is till how much length the fluid is actually continuous in this tube. So from the point of the breakage, the point of the breakage will decide the size of the droplets in the first case.
Team IISER Kolkata, your time's up. The floor is now open to questions from judges.
So you can hear me, right? Two general comments. We need a lot better board work. If there is a question, the first thing you should write is what is the answer to the question. In almost none of them, you did say stuff verbally, so I made furious notes. But it's always better if you write down the answer, then it's up there. I don't have any clarifications because I think I get what all of you said. Could you repeat one thing for me, because I am not entirely sure you did this. So the IIT Bombay team, just go there and in the same stuff that you did, case A and case B, lambda much less than 2 pi r naught and lambda much greater than 2 pi r naught. Can you just quickly say what it is, or you don't have to write, but you can just tell me again.
Yeah, so when
Don't add anything to the board.
lambda is much less than 2 pi r naught, we infer that 2 pi by lambda is much.
I don't need an explanation. I need an answer. When
Yeah, in
lambda
A
is
case, the first case when lambda is much less, then the waves would decay and ultimately die down. And in the second case, we'll get droplets.
okay, we don't have any other questions.
We will now be moving forward with the solution. I request a member from the question making team to come up on the stage and present the solution to the problem.
Hello, am I audible? Okay.
Just this portion.
Okay. So you've got a wave like this. Since you're given the formula for pressure difference, which is delta P is equal to S 1 by R1 plus 1 by R2, and you're given this wave, you're given that the radius changes as R0 plus epsilon cos 2 pi Z by lambda.
So the radius at the highest point will be r naught plus epsilon. Radius at the lowest point will be r naught minus epsilon. That will be one of the radius of the curvature. You also have to consider the other radius of curvature, which is the shape of the perturbations which you are putting on the fluid. Let's say that this particular radius of curvature is some 1 by r. Since this is the mean radius of the fluid, the radius of curvature for the lower section will just be minus 1 by r. So if you want to calculate the pressure difference between, let's say, P1 and P2, P1 will be S into 1 by r naught plus epsilon, okay, plus 1 by r, and P2 will be S 1 by r naught minus epsilon minus 1 by r. If you calculate P1 minus P2, you'll get S into minus 2 epsilon naught by r naught square, because epsilon is much lesser than r naught, and you'll get a term of 2 by r. Now one of the things you have to look for is this particular term of 2 by r. If you have a very small perturbation, if the perturbation's wavelength is very small, that means your radius of curvature is larger. If your radius of curvature is larger, that means that the pressure at 1 is greater than pressure at 2. What will happen because of this is fluid will go from this location to this location, and your perturbation will equilibrate to, perturbation will basically decay with time. One of the other things that you have to consider with this is the rate at which the perturbation will decay with time depends on the gradient of the pressure difference between those two locations. So if you have even lesser lambdas, what happens is your perturbations decay even faster with time. So that's, if you were to, let's say, map out the growth rate with varying lambdas, you know that for very small lambdas they are decaying, so that will be a negative growth rate, and for even lesser lambdas they are decaying even faster. So let's say we draw some sort of dependence which gets even more negative with smaller lambdas. As you look for the case of large lambdas, which are large wavelengths, this term will be lesser, so the dominating term will be minus 2 epsilon naught by r square. Because of that, the pressure at 1 will be lower and pressure at 2 will be higher. This will basically lead to fluid flowing from this location to this location, and this will eventually lead to the formation of droplets. Here you can use that same pressure gradient argument and say that for even larger wavelengths you will have a smaller gradient. Because of that, for very large lambdas, what will happen is your growth rate will keep on decreasing to 0. So you know you have some sort of a dependence like this. Now, just on the basis of this, you can answer the first question, which will be for very small lambdas, it's equilibrating, and for very large lambdas, you're getting droplets. And for the second part of the question, you just have to think that there will be some point at which it will, the growth rate will be 0. There will be some point where it will be maxing out because of this particular dependence you have. On the basis of this, you know that you can't have very small droplets because they have a negative growth rate. You also can't have arbitrarily large droplets because they have a positive growth rate, but the growth rate is much smaller. So whatever will be the lambda for which there will be maximum growth rate, the distribution of droplets will basically be centered somewhere around that lambda max. Because of this, there will be a clustering of the size of droplets around some particular lambdas, and not all wavelengths will give droplets. That will be the answer.
We'll be now going forward with the second question, where IT Bombay will be going first. Et tu, bru-tine. The question is as follows. The crew of the Athena was taking a well-deserved rest day, when all of a sudden a signal of suspiciously feline origin takes over the sound system of the ship. The repair engineer Remus, who was sitting close to the speaker while sipping on his soda, observed something interesting happen in his rig. To study this effect, More clearly, he devises the following setup. Remus fills up a sealed cylindrical plastic vessel of length L with water containing uniformly distributed tiny air bubbles, as shown in figure 1. He connects a speaker on one flat face of the vessel and connects a microphone at the center of the other face. The speaker emits sound of a frequency G such that it created a standing wave in the vessel. First question. How does one bubble move under the influence of the standing wave? Second question. What will be the distribution of bubbles in the vessel look like at the steady state? After the system achieves the steady state distribution of bubbles, Pushkar EL, another crewmate, switches on a uniformly oscillating electric field of the form E is equals to E naught sine 2 pi f dot t. Now the third question is, describe the effect of E on a single bubble. The microphone was set to scan for frequencies of sound of the order of f. Remus observes discrete peaks at certain frequencies after the system achieves steady state again. Fourth question. Explain why he saw discrete peaks and what configurations these peaks correspond to. The assumptions are: ignore gravity, no bubbles are created or destroyed at any time, assumes the bubbles do not merge, the size of the bubbles is smaller than the wavelength of the electric field, the timescale of the motion of the bubbles is lesser than the time period of the speaker sound, the bubbles response to the electric field is in phase with the electric field. IIT Bombay, do you need any clarifications? Seeking no clarifications, we will now begin the time for this question. The time starts now. Team IT Bombay, you have 5 minutes left. One minute to go. IT Bombay, time's up. Please come forward to present the solution. You will have 5 minutes. Your time starts now.
So for the first question, since the tube plastic vessel is sealed from both ends, we have a displacement wave which has a node at both the ends as drawn, and pressure wave has a phase difference of pi by 2 with displacement wave. So we'll have a pressure wave which would have an antinode at both the ends. Then so the pressure wave would follow at the antinodes. It would have pressure of P plus delta P into sine function. And delta P would be maximum at antinodes. So when delta P is positive, like the pressure at an antinode is the highest, then the bubbles would be lesser there, since water has a higher density. And when the pressure is lower, then the bubbles there would be higher. So when it reaches a steady state, the bubbles would be oscillating, and in this case here pressure is higher, so we'll have a higher amount of bubbles here. Then at the node there would be kind of an average number of bubbles, and we would have least here. But when the wave goes through a phase difference of pi, we'll have lower amount of bubbles here, and we'll have a higher amount of bubbles here due to low pressure, and lower amount of bubbles here due to high pressure. Then for the third question, the bubbles would get polarized due to electric field and would perform an SHM, which would have a frequency of F. And then, so the net motion of bubbles would be a superposition of two SHMs of frequency G and F. For fourth question, sure. For fourth question, we can see that so this would be kind of a pressure wave, and here we have a microphone. When the peaks would correspond when both F and G have a maxima near the microphone, like at the end point of this. So yeah, since earlier the speaker has a frequency of G, so the maximas correspond to maximas recorded by the microphone would correspond to those frequencies of G. So if F, which is the frequency of electric field, is an integral multiple of G, that is F equals to Ng, then F would also have a maxima here, which would cause the microphone to detect some discrete peaks corresponding to this F being an integral multiple of Ng. And because like when both maximas happen here it would form a superposition to which would like increase recorded in the microphone.
IIT Bombay, you have 1 minute to go.
And this way.
IT Bombay, your time's up. IT Delhi, come forward to present your solution. Your time starts now.
So the given pressure distribution is something like this. This is delta. So for the first question, if any time the wave is something, the pressure wave is something like this, the bubbles will flow from the pressure of low pressure to high pressure because the water will flow in the opposite direction. So if we consider any here, it will always, and the amount of flow would be directly proportional to the slope of the graph. And here will be like this, and always the flow would be restricted in between these regions, and there would be highest. And for the question 2, the amplitude of the bubbles would be also maximum here, because if we take any region, the amount of bubbles coming here and going from here should always be constant. So if from here the bubble is coming very slowly, so there should be more number of bubbles here and there should be less number of bubbles here. So the bubble distribution would also match to the pressure distribution. It would be something like this, where it is corresponding to the it would correspond to the maximum pressures.
Yeah, this is the distribution of the density of the number density of the bubbles. We have the density of bubbles is least at the pressure nodes, like this. Yeah, for the second part, what we can do is we can consider bubbles like this, and we can consider the ends of the tube like this. What happens is, due to the electric field, the water gets polarized. So we have a surface charge density on the bubble equal to P vector dot n cap. So effectively this behaves like minus plus minus plus minus plus, and the ends of the vessel have plus and minus here. This is this is the charge distribution of the water. So what happens is, when the electric field is maximum in this direction, there is a maximum repulsion from here and here, and this repulsion is such that
30
it
seconds.
compresses most at electric field maximums. So yeah, so we get a sinusoidal compression repulsion like this, and we get maximum received frequency here when the repulsion hits a maximum. At the same time, the sound hits a maximum. So for that we have frequency of electric field by n equal to the frequency of sound.
Time's up. IISER Kolkata, please come forward to present your solution. Your time starts now.
So in this scenario, we can see that the pressure waves are forming a region of sinusoidal regions of high and low pressure, and the bubbles from the high pressure region will get pushed towards the will get pushed towards the low pressure regions, which will result the bubbles in the steady state to be exactly at a phase of pi by 2 from wave configuration. And here, due to the and in the field wave is going to be in a superposition, so we will get peaks from the
Time's
constructive
up.
interference.
IISER Bangalore, please come forward to present your solution. Your time starts now.
So for question number 3, when there is a bubble, and there is an electric field, so the electric field polarizes this, and there will be a net positive charge here and net negative charge here, and the charge distribution will look like sigma naught cos theta, where theta is this angle. So if we look into this configuration, there will be net positive charge here and the plus and minus here, and because of the electric field, this will feel the force like this, while in this part there is negative charge, so the force and the electric field is in this direction, so the force will be like this. The electric field is in this direction, so as there is negative charge, so the electric force is in this direction. So basically there is no net force on it, but the bubble is getting compressed, the bubble is getting elongated, and when E changes the sign, the bubble will get compressed. So the bubble shape will sometimes it will get elongated and sometimes it will be compressed, and the shape will have sinusoidal oscillations. While in number 4, the F equals to will be Ng, because the bubbles will gather at pressure nodes, and to sustain the oscillations, we must have the frequency to be integral multiple of G.
And the pressure and the bubbles concentrate at the pressure nodes
30
because at some time when the pressure is high here and the pressure is low here, they will bubbles will tend to move towards lower pressure. And after time, the same lower pressure zone becomes high pressure zone. So for steady state, after a long time, only the nodes will have a high density of bubbles, and the rest will have a very low. They might not be zero, but they will have a very low density of bubbles, and that leads to the solution for question 3 and 4.
Time's up. The floor is now open to questions from the judges.
Yes, so I want a clarification for the second part. The first question from ISC. Can you just clarify the first one? Where the density of the bubble should be the maximum?
Pressure. So, first, kudos on the better board work. Fantastic. Very good to see a very rapid improvement. What was I going to add? Okay, I think we have the solution, but I don't think any of you addressed what happens to the individual drops themselves, which was also part of the question. So, yeah, maybe in the solution itself, what's yeah, it's fine. You can ask for the solution.
Now we request a member from the question making team to present their solution.
Yeah, so okay, I'll write it. For the first question, you have standing waves in the vessel. The standing waves follow this sort of time variation, and this is the pressure versus distance graph. The force on the bubble is determined by two things. One is the bubble will travel down the pressure gradient. The other thing is that the force on the bubble is proportional to the volume of the bubble, because like it's equivalent to your buoyancy force. If you displace more water, you get more force. So, if you assume that if you locally increase the pressure near a bubble, the bubble's volume decreases, then you can say that, okay, over one cycle, let us consider the volume of the bubble over one cycle of the standing wave. Say a bubble is over here and it has that size. The bubble travels down the pressure gradient. As it is traveling down the pressure gradient, the pressure also decreases because it's a standing wave and it's not at the this is the node, this is the antinode. The pressure gradient decreases, and because of that, the local pressure decreases and the size of the bubble is increasing, right? This process, bubble receives a net rightward force, a net force towards the node. This continues till the pressure is zero everywhere. This is the node, this is the antinode. Bubble size has increased to some positive, like some bigger value than it was started with. And after this, the bubble, the pressure gradient reverses direction because it's a standing wave. If this is the node, this is the antinode. The bubble is now larger in size compared to what it was previously, and so it receives a greater restoring force. Eventually, because of this size imbalance in the size asymmetry in the bubble, you have a net drifting motion towards the antinode. So that's part one. So the bubbles distribution throughout this vessel will be like this. So there's a microphone at the end, but it's a very tiny microphone. You can assume that it does not change the like dynamics of the standing wave. So this is a wall, but this is a speaker. So this is a displacement. So this is a displacement node because it's a wall. It's a rigid wall. But this is a speaker, and hence it's not a distance node. It's a distance antinode. So wherever there are antinodes in the water created by the speaker sound, you will see number density of the bubble speaking there. As for the deformation of the bubble during the in the electric field, this is fine, but there is one more effect that also I think dominates more than that, which is so when a bubble is normally formed, you see dipoles of water randomly oriented, not randomly oriented, oriented in such a way that they hydrogen bond with each other and form this surface, right? If now I switch on an electric field in some direction, a fraction of these will polarize. You only need a fraction for this effect to work. And as they polarize along the direction of the electric field, now the attraction between the molecules in these regions of the bubble will reduce because now they don't preferentially align with themselves to form a maximum attractive surface, but they align in the same direction to so this reduces the surface tension of the water at the poles. And so the pressure, because the pressure is the same, but the surface tension is reduced, the radius will now reduce. The radius of curvature will reduce. That is, the bubble will elongate in the electric field direction. And this will happen whether the electric field is that way or this way. So the frequency of oscillation of the bubble is not F, but 2F. And then, okay, for the last question, you see peaks of frequencies when, so now the bubbles due to the electric field form, arrange themselves at the antinodes of the vessel, and they oscillate with 2F frequency. They oscillate at the same phase because the electric field is uniform and it's acting on the same bubbles throughout. So they act as sound sources periodically spaced with some wavelength determined by G. When these sound sources constructively interfere, the amplitudes sum up and you get an increasing intensity of sound over time. If the amplitudes destructively interfere, or if they don't form a standing wave at all, then you do not you see no sound created by the bubbles. So the peaks correspond to the sound sources, that is the bubbles constructively interfering. Especially if F is very higher than G, then this is exactly what you'll see. You'll see so the sound created by the bubbles will have some very small wavelength, and if an integer number of these wavelengths, which is like given by 2F instead of F, if they fit into the spacing created by the antinodes, then you'll see an amplification. But this assumes that the F is much higher than G. In general, you see peaks only when they constructively interfere, but you can't really predict if the orders of F and G are not relatively matched. That is the answer.
Next, we'll have IIT Delhi going forward with the question, Wo betide you? Wo betide you? The reality bending cat, Professor, comes into view, and the Ethna's crew watches in horror as it plays with their home planet. The planet is of mass m, revolving around a star of mass capital M, where capital M is greater than small m, in a circular orbit. Question 1. Consider both the planet and the star to be point masses, and that the star's location is held fixed. The cat begins to apply a uniform constant force to the planet in a fixed direction in the plane of orbit. The eccentricity of the planet's orbit is observed to increase slightly. Explain this observation with a diagram. Now, instead of assuming a point-sized planet, assume the planet's shape is an ellipsoid. The planet is in a circular orbit around the star, and there is no external force acting on the system. The major axis of the ellipsoidal planet faces the star at all times. That is, it is steadily locked. Suddenly, Professor increases the eccentricity of the orbit such that the rate of rotation of the planet and the time period of revolution remain the same as before. Question 2. If the planet is considered to be perfectly rigid, what will happen to the eccentricity of the orbit over time? Question 3. If the planet is not perfectly rigid, then how does the evolution of the orbit change compared to the previous case? The small constant force, as described in question 1, is now turned on again. Professor looks at the planet's surface and notices large temperature anomalies as shown in figure 1 that persist with time. Assuming the planet is not perfectly rigid, explain the reason for these anomalies. The assumptions are as follows. The planet has no internal heating mechanisms and the star light can be ignored. All objects revolve in the same plane with their axis of rotation perpendicular to this plane. Assumption 3. The material constituting the planet is such that the time scale for deformation of the material is much smaller than the period of revolution of the planet around the sun. IIT Delhi, would you be needing any clarifications regarding the question? Seeing none, you have 15 minutes. Your time starts now. Team IIT Delhi, you have 5 minutes left. Team IIT Delhi, you have 1 minute left. Team, your time's up. Please come forward to the stage and present your solution. You have 5 minutes. Your time starts now.
So initially we have a circular orbit whose eccentricity is 0, and the planet's orbiting, and we apply a force in a direction, say this. So because of this, what happens is that the combination of this and this is such that it does not remain in a circular orbit anymore and slightly deviates this way. Now that this happens, this will again happen at the next instant. So what happens is finally the orbit deviates from the circular path and becomes somewhat ellipsoidal. So yeah, so initially the eccentricity was 0, and after that we have some other value of eccentricity.
So for the question 2, initially the planet was evolving in a circular path, and then since the time period is constant, the new path is something like this. But in the new path, in the question it's given that the rate of rotation is constant. So at some time, the planet would be something like this, which is there would be a inequilibrium between the positions. So it will try to orient itself in something in a way after some time such that there would be such that it would decrease its eccentricity and would orient such that it always becomes tidally logged. But with so eccentricity will decrease in this. And for the third question, because it's not rigid, it can the final orientation will be reached much faster because of the tidal effects, and the rate of and the steady state would have an eccentricity greater than the second case.
So in part 4, I think the reason for this anomalies is also seen in the Jupiter's moon Europa. What happens is due to the combination of the gravitational effects and this force F and the ellipsoidal shape, we have vibrations which compress and elongate the planet as it moves along its orbit. So these compressions create vibrations in the planet's material. Because of these vibrations, it has an uneven heating effect on the surface of the planet, and thus we have regions which are colder, hotter, etc.
Since you have a couple of minutes, can you do one thing? Just answer one. Just draw the new orbit. Okay. Question 1. You have a couple of minutes. Since he erased some stuff here,
Yeah, it's not. This point becomes closer. Yeah, this is more accurate.
IIT Delhi, you have 1 minute left. IIT Delhi, your time's up. Next up, we have IISER Kolkata. You have 3 minutes and your time starts now.
So basically in the first question, what is happening is that the star's location is held fixed. Now, when the cat is applying a uniform constant force to the planet in a fixed direction to the orbit, so there the centripetal forces are in the direction, in the radial direction inwards, while the cat is applying a constant force in one direction. What is happening is that the centripetal force over here is being cancelled somehow, I mean somewhat, by the forces, by the constant forces being applied by the cat, whereas over here the centripetal forces are increasing, centripetal forces and the constant forces adding up, which is leading to the orbit being shifted over here and the orbit being elongated on the other side, leading to two focus and the eccentricity increases. So this is the reason for the slight increase of eccentricity for part number 1. So the new orbit becomes somewhat like this over here.
In the second part, as the eccentricity of the orbit is increased and the time period is actually maintained the same, this has to come down to this, that in the parts which are covering longer distance, the planet has to move faster than the parts where the planet has to move slower. So in the parts the planet so in the parts where the planet has to move faster, it is experiencing a greater centrifugal force than the planet, than the parts which in which it has to move slower. So over time the eccentricity is going to a bit, and it will to try to again reach the steady circular state.
For the fourth question, as the small constant force is turned on again, so what is happening is basically, since the planet is not perfectly rigid, now because it is tidally locked, this face that facing the sun, it always faces the sun, so it has the hot temperature. Since again it is not perfectly rigid, so what is happening is that it deviates a bit, the planet, the surface deviates a bit, deforms a bit, and when it moves away from the through the eccentric pathway, then it goes away from the sun, so it becomes a little bit colder, but then the material again constricts, and by the time it again comes, so the other surface is already hotter, so it is a hot cold type thing on the orbit for the ellipsoid.
Your time's up. Next up, we have ISC. Your time starts now.
Okay, so I shall begin with the deformation of the planet for cases 2 and 3 where the planet is not rigid. In the sorry? Huh? Yeah, why one? In case of the non-rigid planet, when the planet is at the perihelion, it would have the maximum eccentricity, the planet itself. When it moves further away, because the eccentricity in this case is not because of the planet's rotation, which is negligible, it is because of the star's gravity. As it goes far away, because of the gravitational effect decreasing, the eccentricity of the planet itself decreases. It becomes less ellipsoidal, and since the rate of rotation of the planet doesn't change, whereas the velocity of the planet is faster here and slower here, so the tidal locking does not hold as the the rotation of the planet and the revolution fall out of phase. Hence, at a point between the perihelion and the aphelion, it will not be tidally locked anymore. At such points, it will the gravity will try to squeeze it again so that it reaches more of a tidally locked position. In doing that, the axis of the ellipsoid itself changes, which causes the planet to deform. The deformation itself to move in a circular manner. So that causes the insides of the planet to move in convections, and that leads to plumes, which increase the surface temperature. The increase in temperature will be hottest near the equator of the planet, and the increase in temperature goes down as we go towards the poles.
In question number 1, we have that because of this force, the planet will have velocity in this direction. So basically, the eccentricity increases in this direction.
In question 3 for tidal, since it's not perfectly rigid, the tidal motion
Your
on
time's
the
up. IIT Bombay, your time starts now.
For the first question, the constant force can be thought of that a very high mass is kept at an infinite distance, and the force is along it, and this will cause the orbit to be such that it will become elliptical, and this will be closer to that very high mass, and the major axis of that orbit will be along the force, which will be because of the very high mass which is at an infinite distance. So this is how we can think about the very first question.
Yeah. For the second question, I am taking x to be the semi-major axis of the ellipse and r to be the initial radius of the planet, the circular planet. So like whenever the planet goes, this is capital R, and there would be a different force than what it would have been if it would be circular. So by solving the equation, we get a force that is proportional to r cube. The equation would be sort of 1 by r minus x square plus 1 by r plus x square by r minus r square. But here the velocity is significantly lower than what it would be here. So the change of the aphelion of the planet would be faster than what it would be here. Hence, it would
30 seconds.
Kind of decrease the eccentricity and ultimately form a circular orbit. In the third question, it would just happen faster because the planet would become slowly more and more ellipsoid. In the fourth question, we can take a similar case, Jupiter and its moon, and when it goes closer to the sun, it would be acted by the tidal forces of sun. Here, the tidal forces of sun would be less. It would cause...
Your time's up. The floor is now open to question from the judges. Seeing none, now I would like to invite a member from the question making team to present solution to the problem.
Hello? Okay. Let's say this is the constant force which is acting on the orbit. This is your capital M, which is the sun, and the small m, which is the planet. To determine what kind of shape this orbit evolves into, you have to consider these 4 points, A, B, C, D. Now, in this case, what you are basically doing is you're providing a thrust, which is, let's say this is rotating along this direction, then you're providing a thrust which is in the same direction as the direction of your velocity. What this leads to is a eccentricity increase in the opposite direction. So your point C moves away. Now, if you are considering the location here, then the velocity is in this direction and you are providing a retrograde thrust. Because of this, this point A moves inwards, because if you are decreasing the velocity here, the velocity will be pointed in radially inwards, and this will lead to the point getting in comparatively of lesser radius than what it was before. If you consider points B and D, then at point D what you are effectively doing is you are again moving this radially inwards because of this small constant force, and you are moving this radially outwards. Now let's say you consider any elliptical orbit. The characteristic of the elliptical orbit will be that at the closest point and the farthest point, those are the only 2 points where there will be a tangential velocity with respect to the central force, and at any location which is in line with the sun, the velocities are radially outward and radially inward. So what happens because of this force is that eccentricity will not increase in the same direction as the force, it will increase somewhat roughly perpendicular to the force. So the final orbit actually looks more like this. Now, if you consider the second question, if you have a rigid ellipsoid moon and your orbit ellipticity has increased, you have to consider these 2 points, the farthest point and the closest point. Since your rotation earlier it was tidally locked, so its rotation rate and revolution rate were the same. Here, since its ellipticity has increased, its revolution rate is greater. What happens because of this is there will be a lagging of the rotation of the tidal bulges on the planet. Because of this, if you consider the forces on the 2 tidal bulges, this force and this force, what you have essentially got, since this force is stronger because this tidal bulge is the one which is pointing comparatively closer to the sun, what you have essentially got is a retardation on the orbit at this point. And at the opposite point, the opposite effect happens because your tidal bulge will be comparatively pointed ahead because its rotation rate will be faster than its revolution rate. So because of this, what happens over a large period of time, over many revolutions, will be your orbit will become circular. What happens in the case of it being not perfectly rigid is you'll allow, since it's rigid, you can't have any motion within the planet itself. If it's not perfectly rigid, you can allow the tidal bulge to rotate slightly in the direction of the central force. Because of this, if you have made this orbit elliptical same as the case before, the effective tidal forces which are acting on this planet, which are leading to it becoming, which are leading the orbit to become circular over time, is decreased. Because of that, the time scale at which circularization will happen will actually increase. And what happens in the fourth question is, since there are 2 effects happening. The constant force is making the orbit more elliptical, and the tidal forces are basically circularizing the orbit. So what happens when you first start the constant forces, the orbit will become elliptical. At some point, the tidal forces will start determining the evolution of the orbit because the tidal force depends on the extent of the tidal lag of the planet. And you basically get oscillations of ellipticity around some non-zero ellipticity. And because of those oscillations, there's continuous deformations of the planet, which will eventually lead to heating of the planet.
Now moving forward, we have the last question. Everything, everywhere, all at once. And we'll be going forward with IISER Kolkata going as first. The question is as follows. Back on the cruise planet, RUPSA is conducting an experiment to measure the Rayleigh scattering from a single molecule placed at the origin. The scattered light has the same wavelength as the incoming light. The results are shown in figure 1. Here's the description for figure 1. The red ray represents the incoming light propagating in the positive x direction and polarized along z. The scattered light is emitted in all directions as shown by blue rays. The observed intensity along a given direction is proportional to the distance to the green beagle in that direction. The polarization of the scattered light has a component parallel to that of the incident light. There is no propagation of the scattered light along the positive z direction, that is, the intensity is 0. Next, they perform a second experiment whose setup is as shown in figure 2. And here's the description for figure 2. The gray sphere is a vessel containing an idle gas. A blue tube is attached to the vessel and a detector is placed at the far end of the blue tube to measure the intensity of scattered light. The tube is long and thin enough to ensure that only light propagating parallel to the direction theta, phi can reach the detector. Now, a beam of light polarized in the z direction is incident onto the transparent chamber. To their surprise, RUPSA noticed that even at theta is equals to 0 and theta is equals to pi, there was some intensity of scattered light, while the maximum still occurred for theta is equals to pi by 2. First question. Explain the observations in the second experiment considering that only really scattered light is emanating from the chamber. The detector can also measure the direction of the dominant polarization by rotating a linear polarizing filter attached in the blue tube and recording the angles at which the maximum intensity and the minimum intensity occur. The degree of polarization D for a particular theta comma phi is calculated as D is equals to Imax minus Imin upon Imax plus Imin, where D is between 0 and 1. Second question. In both the experiments, explain how D varies with theta and phi. Rupsa receives news from the crew that the planet will not survive Prophesus much longer, and that she has only 1 day left to complete her last experiment before it is destroyed. Curious about the polarization of the scattered blue light of the sky, Rupsa disconnected the tube from the chamber. She went to a barren salt lake before sunrise, placed the detector parallel to the ground. There were no trees or buildings, so the line of sight of the detector extended to the horizon. The detector tube was oriented along the northeast direction. At 6 a.m., the sun rose directly from the east, at 12 p.m. was directly above the detector, and at 6 p.m. the sun set in the west. Third question. How does D change over this period? The assumptions are ignore Doppler shift due to the motion of the molecules. IISER Kolkata team, do you have any questions? Seeking no questions, the time starts now. Team IISER Kolkata, you have 5 minutes to go. One minute to go. As a Kolkata, your time's over. Please come forward to present your solution. Your time starts now.
For the first question. For the first question, for the second experiment, when the Rayleigh scattered light is emanating from the chamber consisting of ideal gas, what is happening is basically that suppose there is an ideal gas molecule, the polarized light in the z direction is coming, getting scattered by this ideal gas molecule in a certain random direction, after which there is also a probability of some other ideal gas molecule in the path, and then there is a probability of going parallel to the z direction, which is why we can get certain intensity of light in the z direction, which is why we are getting something. And obviously in the pi by 2 at an angle of theta is equal to pi by 2, there will be the maximum intensity of scattered light, simply because most of the light goes unscattered. For the second question, the detector, when it is So for the second question, the degree of polarization depends on the value of Imax and Imin for a particular, for both the experiments. So in the first experiment, the intensity of the light is varying with the angle theta, as in like, it is a Dirac delta function. So there is no scattering observed in the angle theta is equal to 0 and theta is equal to pi. But for the second experiment, as we can see, there is a broadening because of the explanation from question number 1, which is why the d value being Imax minus Imin upon Imax plus Imin for the first experiment is almost constant for all the angles regardless. But for the second question, since the value of Imax and Imin for a particular angle is different, so it will vary over time. It will oscillate depending on where the Imax and Imin would be. I mean, that would obviously be random because it has a random possibility of how much Imax and Imin can be. Third question.
In question number 3, we have the sun going from east, then it is directly above the then it is directly above the detector, and it goes towards the west. So in these positions, we are going to have the least scattered light being received by our detector, and when it is like when it is like directly overhead to our detector, it is going to receive the light. So as the formula for the degree of polarizability is Imax minus Imin by Imax plus Imin. So we are going to have the maximum difference between Imax and Imin when we are receiving the least scattered light. So the value of D will be the highest in the morning and during the sunset, and we are going to have the minimum value of D when Imax is almost equal to Imin, means when it is like when it is directly overhead to us. So the plot will look something like this, D over time.
As Kolkata, your time is over. Next, we have IISc Bangalore. Your time starts now.
In the first question, question in the first question, we see that in the second experiment there is some scattering, there is some light in the theta equals to 0 and pi direction also, which does not happen in the first case. So because suppose there is an ideal gas molecule here and the light is coming in this direction. Now after getting scattered from here, it will be something like this. And although there is no light in along the z axis for this molecule, it may hit some ideal gas molecule in this in this direction, and then the light will get scattered again, and so there will be component then the light will get scattered from here again, and then along the vertical axis of this there will be no scattering, but all along all the other directions there will be some scattering. So along the original z direction there is some scattering. So we see that along theta equals to 0 and pi, instead of the light intensity becoming 0, we have some light intensity. Although because most of the light is going unscattered, so at theta equals to pi by 2, still we will have the intensity maximum. And for the second question, in the first experiment, the D will vary with angle like this. Because at theta equals to 0 and pi, in the first experiment the intensity is 0, so I max equals to I min equals to 0, so D will be obviously 0. And at theta equals to pi by 2, that means in the direction of the scattered light there is random scattering all along the xy plane. So the polarization, as the light is scattered all along, there will be maximum difference between I max and I min because it is all random. So D will be maximum at that point. And in the second experiment, we see that in the second experiment we see that when we vary D with angle, the graph should be shifted vertically upwards, because in the earlier case I max equals to I min was coming to be 0, but now we have some intensity along the z direction, and there should be some polarization also, because light is coming in this direction and light along the direction. The polarization something will like this, but there will the only polarization will not be along z direction. There will be polarization along other directions also. So but because the intensity will be less, so the I max minus I min value will be smaller. So D will be smaller at 0 and pi, but it will have some positive value unlike the other case.
Your time's over. IT Bombay, please come forward to present your solution. Your time starts now.
For the first question, we have, since it's gas, very less amount of space would be occupied by molecules. So most of the rays would not scatter due to a molecule or just hit one molecule. Very few would hit another molecule and then can scatter in the z direction or anywhere else. So that's why we are seeing some amount of light in the z direction also. Then to calculate in the first experiment, there is no light going in the z direction, which corresponds to theta equal to 0 or pi. So we'll have a graph like this, and pi by 2, we have all the scatterings, we have all the polarizing already in the z direction. Then in this scenario, we'll here it is 1. We'll have a graph like this, which would be above 0 because some of the light can still go in the direction of theta equals to pi by 2 after scattering. So it won't be completely polarized. And it would be independent of phi due to symmetry. For the last question, we have a detector like this. This is the zenith, north, east, and west. So one thing I have to notice here is that unlike the first two scenarios where we
30 seconds to go.
where we already have a polarized light, here we don't have a light which is already polarized. So, but when the sun comes from zenith, we'll like there would be more scattering because whatever light comes in the detector is goes through a lot of different direction changes. So when the sun is at zenith, there would be D would be less, and at other points it would
Time's
be
up.
more.
IT Delhi, please come forward to present your solution. Your time starts now.
So for question 1, light always scatters in the plane perpendicular to the plane of electric field. So for the first scattering which will occur in the xy plane. So the first, and this will also have a perpendicular component of the electric field which is not along the z direction. So the next scattering which would occur will occur in the plane which is not xy plane but some random plane. So after many scatterings, it can go at any theta and phi. And since all of them have electric field component and the z direction, the maximum intensity would be at theta equal to pi by 2 and the minimum would be at 0 and pi. And for question 2, for the first case at theta equal to 0 and pi, there will be only one component of electric field. So always the Imax and I mean detected by the detector would be same. So for 0 and pi, it would be 0 and the maximum would be at pi by 2.
Thirty seconds. Time's up. The floor is now open for questions by judges. Seeking no questions by judges, we will now request a member of the question making team to present the solution.
Hello. So most of you were able to understand that multiple scattering will produce some intensity at theta equal to 0 and pi. I felt that many of you misinterpreted what degree of polarization means. All right. For question 2, the first case is just a single molecule. A single molecule, we had given the pattern of intensity. But in any given direction, there is only a single polarization of light in that direction. So the single molecule is a trivial case where the degree of polarization is not going to change with theta or phi. It's just going to stay at a constant 1. There's only one polarization of light produced in that direction. So if I rotated a filter, if I held from some theta phi, if I measure the degree of polarization, I would only detect one linear polarization of light. And so at every theta phi, the degree of polarization is 1. Things get a little messier with multiple molecules in the picture. But we can use some symmetry to figure things out. Okay, so we figured out that there is some intensity going at theta equal to 0 and theta equal to pi. So this is the circular chamber. We had light coming in from some direction. But the first scattering intensity pattern forms these bagels. If the detector is placed here, we know that no direct scattered light can reach here because no single molecule is going to make light which goes in the theta equal to 0 direction. So we have to look at the second scattering. If you look at the second scattering, we see that if these are the first hit molecules with the incident light, a molecule hit here, sorry, a molecule hit here could have some random angle of polarization, so it produces some intensity. But because the chamber is symmetric in phi, you will not get any favored direction of polarization, and so for the chamber, you will have some maximum degree of so you will have degree of polarization 0 because there's no favored direction at theta equal to 0 and pi. You will have some maximum and it will come back to 0. It cannot be entirely 1 either because even if I place my detector somewhere in the xy plane, I will have, so I will mostly have just the vertical component, but I will also get some bleeding from the horizontal component because of the multiple scattering effect. Okay. The last part was sunlight. So the unpolarized light from the sun still produces some permanent polarization because, so first we'll consider 6 a.m. or 6 p.m. The incident rays are grazing the surface, they're coming parallelly from that direction. So the angle of polarization is either up down or it's into the plane. Light which is polarized into the plane can scatter from here, and directly scattered light can make it to the detector. So you will have, so here the intensity is maximized, but for vertically polarized light, in our reference, you will have a lower intensity produced at this angle, and so the and so at 6 a.m. or 6 p.m. you have some bias towards vertically polarized light, and there is less intensity of horizontally polarized light, and so you have some degree of polarization, not close to 0 but not close to 1 either, at both 6 a.m. and 6 p.m. At noon, you have the maximum polarization because now light is coming from directly overhead, which in this case I would represent like this. And so the angle of polarization is some of these two components. But the scattered light that's produced from these molecules, if it happens to head in this direction to the detector, all of these components will just be horizontally scattered light. So you have this constructive effect because you don't care about the original degree of polarization. The component that will reach your detector is going to be horizontally polarized, but because of multiple scattering, again, you will have some kind of dampening. So you will have this. Okay, all right. Any doubts?
With that, we conclude the deep thought round for physics Mimamsa.
Avtar, can I say a few things?
Yeah, sure.
So let me just, on behalf of both Surbhi and me. So the first thing is, these questions like sort of gestate over, sometimes days, sometimes weeks. A lot of time goes into maybe perhaps the language itself, but nevertheless, it takes some time for them to come about. So it is always impressive to us that in 15 minutes you are able to get to the heart of the problem that fast, right? So first, congratulations for that. That's really amazing to see. Also, a small shout out to the IIT Bombay team for having gender diversity. I'm very happy about that. The third thing is, yes, indeed. It does seem that you're not taking full advantage of the scheme of things. So, for example, now we've erased the board, especially if you look at in this last problem, IISER Kolkata answered the first part, and then each of you repeated the first part again. What were you hoping to get out of repeating the same answer again? You're not going to get any marks, even if you're right. So what should actually be happening is when the other teams are presenting, I should be open. What are the facts they are missing? And make it a point that if you're the second person answering, use your 3 minutes wisely. Don't repeat the stuff that they got right or that you're going to say the same thing again. Instead, focus on, okay, look, they didn't say this, so I'm going to add this point, and I'm going to add this point, and so on. And that's how you will try to, extract marks. And that's how you can make the most out of those 3 minutes rather than spending time in trying to give the same answer again. So you have a couple of deep thoughts left, or one, two more. So maybe it helps you for those two. Okay, and then congratulations again. Wonderful.
Thank you so much, everyone. Firstly, I would once again like to extend my gratitude to Professor Saurabh Dubey and Dr. Surbhi Jaiswal for being our judges for this round. And also a couple of quick announcements. Now we'll be having lunch served in the guest house dining area. So I would request all the participants and their team coordinators, the judges, and of course the physics question making volunteers. So after your discussion is over, you can proceed to the guest house dining area. Meanwhile, the team coordinators and the participants can move towards the guest house. We'll be having lunch there.
Make all announcements.
One more thing before the participants leave, we would like to explain the titles of the questions. If you would, okay, I'll explain it. It'll take 2 minutes. The first thing is rest in pieces. The obvious reference is the stream breaks into droplets, but the hidden reference is to the type of instability that causes the droplets forming is called a plateau-Rayleigh instability by two guys called Plateau and Rayleigh. So PRI gets permuted to RIP. Bad. Okay. The second thing is called et tu, Brute, which, if anyone has read Julius Caesar by Shakespeare, are like the last words of some of the last words of Julius Caesar before he stabbed in the back. Why Caesar? It's because so in the last part of the question we saw that some frequencies were getting amplified. So this is very equivalent to what happens in something called a free electron laser, because of different reasons. But the point is, this device, this theoretical bubbles in a cylinder, is called a Caesar. Hence Caesar et tu, Brute. Okay, very bad again. The next thing is Vobitidio would be the most obvious one, because Vobitidio is like may you go to hell or some equivalent of that, and they are tidal forces, so Vobitidio. Last is everything everywhere all at once is because light. Two things, because light was getting scattered in every direction, and that was the cool thing. And the other part is the intensity profile of the Rayleigh scattered light was a bagel. So everything bagel, if you've seen the movie, you would get the reference. Yeah, that was the title hints. You do it.